Hello friends. Today in this video we are going to see about Gauss law. So if you came to this video, you would probably know what is electric flux. So it's nothing but it is directly proportional to the number of field lines per some for some area. So now we are going to discuss about one important theorem that is given by Gauss. So we can call it as Gauss law or Gauss theorem. So what is this Gauss law or Gauss theorem? So let us see about it. Okay, first let us take some closed surface like this. Okay, so let me say that there is a charge q1 here, a charge q2 is here, a charge q3 is here, a charge q4 is here. Let me just assume these charges are there. So what is our goal now is to find the electric flux that is passing through our surface. So here we need to find the electric flux of this surface. So how are we going to do that? Okay, if you go by the definition of electric flux, you will know that flux is equal to electric field vector dot A vector. So since this is a continuous body and the electric field and the area are changing continuously throughout the surface, we are going to take a small part of this and then integrate it to the whole surface. That is our conventional approach according to the definition of flux. So what will we do? We will just take a small flux as equal to integration of some electric field at that point, whichever small point we are taking, this point let us say, and the small area that we are taking, which is this area, which is denoted by del A. So if we integrate all the flux for this, all the surface area of this entire body, then we will get the net flux. So like this. Okay. So now what we need to do? We need to find the net flux. The thing about this is, you see, at every point the electric field is like keep on changing, but there is no definite pattern or something that we can like quickly see from this figure. So for example, if you take at this point, this point, this point, this point, this point, electric field is there due to this point, due to this point, due to this point, due to this point. Every point there is electric field due to all those charges, and it becomes really quite complicated and like tough to calculate all these electric field and then do the integration and all those things. And even if you put the limits, since it is a closed surface area, usually for integration you will put a limit like this, like something from A to B or something like that. But the thing is, this is a closed body, that is a closed surface area. Because of that, wherever you are starting, you go all around the body and you come back to the same point. But if you put the same variable here and here, then it will just become zero, right? So that is why we use a special notation, that is we put a circle here in this f kind of symbol. So this denotes the closed integral, closed integration. Yeah, anyway, but we can't do this integration directly, that is without any formula or without any new stuff, so it's like very, very difficult. So what do we do here? So to our help there comes Gauss law. Gauss law provides a really simple and like easy way to find the flux in this kind of situation. So what does Gauss law say? Let us see that now. Gauss law says that the net flux through a closed body, it is equal to the charge enclosed by that body divided by epsilon naught. So let us sink that in for a moment. The net electric flux for a closed body, that is phi, that is equal to charge enclosed by epsilon naught. So let us take this example here. So what is the charge enclosed here? The charge enclosed is nothing but the charge that is present inside the body. So in our case, the charge that is present in this guy, in this surface area, what is the charge present? That is our charge enclosed. As you can see, there is q1 and q2 here. So according to Gauss law, net flux is equal to charge enclosed by epsilon naught, which is equal to q1 plus q2 by epsilon naught. It is as simple as that. You see here this thing, this entire integration, it was like so complicated, right? There are so many points, there are so many electric field at each point, we simply couldn't calculate it. But see, as given by Gauss law, it is nothing but the charge enclosed by epsilon naught, that is q1 plus q2 by epsilon naught. It is as simple as that. So that is why we need Gauss law. Using Gauss law, we can easily calculate the electric flux for a closed surface area. So let us write the formal definition of Gauss law below. Gauss law is nothing but the net electric flux on a closed surface is the charge enclosed by epsilon naught. So that is the written statement of Gauss law. So let us write the formula here now. Net flux is equal to Q enclosed divided by epsilon naught. So this net flux we also can write it as in this way that we have first tried to do that. In that way also we can write. So this net flux is equal to closed integral of E vector dot del A vector. This is also in vector notation because it is a dot product. So this is the definition of Gauss law. So there are a couple of things that you need to remember. The first thing is that this is giving only the net flux. Okay, so we do not know the flux due to each of. Let us go back to our example. We do not know the flux due to this one, this one, this. I mean, sorry, not this one. This one, this one, this one, this one. We do not know the individual flux, but as a net flux we know that it is due to this and this, and it is given by this expression. Another thing that you should notice is in this formula, as you can see here, this E vector is nothing but the net electric field. So this is E net. That implies that at every point you are calculating the electric field due to all the four charge particles that we are having. So due to all these electric field together only, we are saying that this flux is equal to this value. So you should not consider the electric field of only this Q1 or Q2. No, 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 no. It's not said by Gauss like that. It has been said that you should consider all these other charges also in the entire system, but together whatever you do, the net electric field into the area integration will always give you the Q enclosed by epsilon naught. I hope you understood this concept. See you next time.